まずご登壇いただくマーチン・ヘッド先生のご紹介をさせていただきます。マーチン・ヘッド氏はカナダのトロント大学およびブロック大学の教授であります。花粉学や層序学を専門とし、渦弁妄想が記録する新生代後期までのあらゆる記録の解明や第4期の正式な細分化に取り組んでおられます。また、国際層序委員第4期層序小委員会の委員長を経て、現在は同委員の副委員長、また、中期後期更新生協会の作業部会の共同コンビーナや、同委員会における人新世作業部会、国際層序区分小委員会の委員、国際第4期学連合の諮問委員を兼任しておられます。また、チバニアンにおける GSSP の承認の際には、前期、中期更新生協会に、おける第4期層序小委員会の作業部会の共同議長を務めておられました。それではマーチン・ヘッド先生にお願いいたします。
Okay, well, thank you very much indeed for the kind words and the warm welcome. And it's a great pleasure to be here at Ibaraki University. Well, my talk is going to be a little bit broader than the title that is shown in front of you. I'm going to introduce the Anthropocene from a rather general perspective, and then I shall focus on certain specific themes. Okay, so essentially then, my talk is going to detail the Anthropocene, essentially the evolution of an idea. Then I'll be talking about the Great Acceleration, and I'll explain what the Great Acceleration is and how important the Great Acceleration is to the Anthropocene concept. I'll then talk about an event approach, a geological event approach, which has been suggested as a replacement for what we would call the chronostratigraphic Anthropocene. And finally, I'll explain how we within the Anthropocene working group are working towards defining the Anthropocene as an official unit within the geological timescale. And I'll also be updating you with the very latest developments. Okay, well, the Anthropocene was first introduced as a term by Paul Crutzen, who was a Nobel laureate and an atmospheric chemist. And he belonged to the Earth system community. That is, this is the community of scientists who are looking at the Earth, examining the Earth as an integrated system. And he introduced the term Anthropocene to emphasize the central role of mankind in geology, proposing the term Anthropocene for the current geological epoch. Now, epoch here is important because we are currently living in the Holocene epoch. So his notion of the Anthropocene was that we had left the, if you like, the normal envelope of variability of the Holocene, and we were now in a new epoch, the Anthropocene. So this is the current official system, the current time scale in which the Holocene is above the Pleistocene. It's part of the Quaternary. It's a series and epoch, and we are currently living in the Holocene. But the proposal by Paul Crutzen was that we have actually left the Holocene and we are now in a new series and epoch known as the Anthropocene. So the Anthropocene, according to Paul Crutzen, has terminated the Holocene. Now remember that this was a concept that originated within the Earth system community. The question is, does the Anthropocene have, if you like, a geological reality? And remember, the geological timescale is defined by geologists. So it's used by many other people, but it is defined by geologists, and it is defined using geological criteria. So therefore, examining the Anthropocene from a geological perspective is crucial to the entire enterprise. This paper came out in 2008. Are we living in the Anthropocene? And it was co-authored by Jan Zalasevich and others, both geologists. And it gave rise, essentially, it brought the Anthropocene to the attention of the geological community. And as a result of that, the Anthropocene Working Group was set up with Jan Zalasevich as chair of the working group and Colin Waters as secretary. This is the working group of the International Subcommission on Quaternary Stratigraphy. There's quite a lot of bureaucracy involved in this because we are dealing with both normal science, where you are looking at data and ideas are driven and tested by data, and normative science, where you are essentially determining classifications, and the criterion for whether a classification is good or not is whether it is workable or not. So this is normative science. One of the first questions you have to ask, at least as a geologist, is when should the Anthropocene begin? Well, there have been a number of proposals, including one suggesting that the latest Pleistocene is when the Anthropocene should have begun. And this would coincide with the extinction of megafauna as a result of human predation, going back maybe 50,000 years. However, Paul Crutzen, when he proposed the idea of the Anthropocene, he suggested the beginning of the Industrial Revolution in Europe. Now, for a unit within the geological timescale to be workable, it has to be traceable, or at least the base has to be traceable on a global scale. The problem with the Industrial Revolution is, although it left many geological markers in Europe around the 1870s, the Industrial Revolution was not an isochronous global event. In fact, in Japan, it didn't start until about the 1860s. So we couldn't really use the Industrial Revolution to define the base of the Anthropocene. What is useful is the so-called Great Acceleration, and I'll be speaking a bit more about that. The Great Acceleration refers to an upturn in many socioeconomic trends and their geological indicators in the mid-20th century, specifically immediately after World War II. You had globalization and you had industrialization on a major scale. All sorts of things happened immediately after World War II that gave rise to a change in the global system and also provided a lot of geological signatures within the sedimentary record that can be used for global correlation. Another important marker is in 1952. Here we have a rise in the dispersal of plutonium-239, which is a fallout product from the testing of thermonuclear devices. And this is a bomb test fallout, which is global in extent. Now, of course, 1952 falls within the mid-20th century. So these two, if you like, sets of signals are complementary to one another. Okay, so speaking of the Great Acceleration, the actual term itself, Great Acceleration, was coined not by a scientist, but by a historian, John R. McNeill, an American historian, a historian of environmental change during the 20th century. And the historians, in a sense, knew about the Great Acceleration before the scientists had actually tested it and looked for it in the data record. But the concept behind the Great Acceleration actually arose from Earth system science. And it was Will Stephan from the Australian National University who had been examining a number of records, a whole raft of records of environmental change. And he realized that there was a major upturn in various signals around about the mid-20th century. So the concept of the Great Acceleration comes from Earth system science. And it was Will Stephan who really pioneered the understanding of the Anthropocene from an Earth system perspective. And he published these curves known as the Great Acceleration curves. And they show a number of different indicators, whether it's methane concentration or CO2 concentration, the consumption of fertilizer, the number of McDonald's restaurants going down in Russia right now, of course, but elsewhere still flourishing. And all of these indicators show an upturn at or around 1950. In other words, the mid-20th century. Now, the Earth system science approach is that we are already in the Anthropocene, that the Anthropocene began in the mid-20th century. And that essentially what has happened is that the Earth has moved, it's shifted from if you like, a normal interglacial state representing the Holocene. It has shifted into something that is different, something that we have not seen for at least 800,000 years. We've moved into a new state, and we are heading actually down across a planetary threshold. We are now in the Anthropocene. We have left if you like, the normal envelope of Holocene variability. We are now into something completely different. We can either continue down into a semi-permanent hothouse world, or with responsible planetary stewardship, we can shift the course of the planet back into a stabilized state. Anyway, so the Earth system science approach is that the Anthropocene began with the Great Acceleration. Now, this is being explored and has been explored by geologists, geoscientists. And the evidence for the geological Anthropocene has been summarized in this paper that was published a couple of years ago, The Anthropocene as a Geological Time Unit. Among the Anthropocene signatures that we can use to identify the Anthropocene as a geological term are things like novel mineral-like compounds, of which there are more than 180,000. Fly ash, black carbon, microplastics, metals, chemical signatures, stable isotopes, radiogenic isotopes, and biotic signals, that is, extinctions of species and the translocations of species from one continent to another. These all allow us as geologists to define an Anthropocene from a geological earth sciences perspective. So importantly then, the Great Acceleration aligns Earth system and geological definitions of the Anthropocene. It provides a mid-20th century inception for the Anthropocene. And as I'll show you in a few slides from now, it justifies the rank of Anthropocene at the level of epoch, which then means that it terminates the Holocene. And in 2016, the Anthropocene Working Group recommended that the base of the Anthropocene be defined by stratigraphic signals associated with the mid-20th century. just to underscore the importance of changes that took place in the mid-20th century. Look at the three main drivers of environmental change: global population, global energy consumption, and global productivity. They all show very sharp upturns around about 1950. In fact, if you look at global energy consumption, we see a profound upturn at around 1950. And this is a sobering thought when you look at not just the rate of change, but also the magnitude of change. The magnitude of change is illustrated by this very simple fact. More energy has been expended during the Anthropocene, that is the last 72 years, more energy expended during the Anthropocene than for the entire Holocene. 22 zetajoules, mostly fossil fuel burning. In other words, since the mid-20th century, we have been going through energy as a massive energy burn. We are burning our way through the environment. And this has all happened since the mid-20th century. Now, I should explain that when I talk about the Great Acceleration, I don't mean acceleration in the physics sense or the mathematical sense. And the curves show you that this is not actually a strict mathematical acceleration. If you look at the annual growth, for example, growth rate of energy consumption, or GDP per capita, or average growth rate of population, we're not seeing an exponential rate of increase. But what we are seeing is a rapid increase, and we are seeing sustained positive growth rates. That's the crucial thing. Rapid change at around the mid-20th century, and then sustained positive growth rates. And this leads to massive increases in magnitude, and it is the magnitude of change that has overwhelmed the planetary regulatory systems. Of course, this was predicted quite a while ago. It's impossible to maintain an acceleration because eventually you deplete whatever resources you're trying to exploit. So the acceleration can't continue forever. But the inflection point, which is where acceleration, if you like, slows down, occurs at around about the mid-20th century. And in some cases, you have continued growth, rapid growth, for example, in atmospheric carbon dioxide. Some indicators of planetary change, for example, fish catches, cannot possibly be sustained over the long term because fish stocks become depleted over time. So you get a slowing in the rate of fish catches. This is to be expected. If we look at cement production rates haven't actually increased since 2015, but the amount of cement used and the impacts on the Earth system are both cumulative and they are lasting. The amount of cement produced per year increased 32 times between 1950 and 2015. And even though increases or the production of cement has leveled off, the amount, the actual sheer magnitude of cement within the Earth system is so vast, it is going to have a lasting effect. Something to bear in mind is that cement production, one, releases very large amounts of CO2 into the atmosphere. Secondly, by quarrying all of the materials we need to make concrete, we are increasing the flow of sediment into the nearshore marine realm. And thirdly, are of course producing an enduring rock-like substrate that will last from a geological perspective. It will last for a very long time. Okay, so generally then, with respect to the great acceleration phenomenon, you have rapid growth at around 1950, but it's inevitably time limited. So the term acceleration is figurative. But even after 1950, growth remains positive, and you have overwhelming magnitudes reached rapidly in the mid-20th century. In a sense, you can say that the Anthropocene is not so much a matter of human impacts themselves. The Anthropocene really represents the Earth system's response to those anthropogenic impacts. It is the Earth system's response that is really important. It doesn't really matter whether it was humans that were impacting the Earth system or not. The fact is, it's the Earth system itself that has been perturbed. And again, just to highlight things, it's the enormous increase in magnitude that are the key features of the Great Acceleration. These are relative increases since 1950, going from 1950 to 2015. For example, copper production has increased by 703%, iron and steel production by 765%, aluminum production by 2,800%, and so on. So it's this overwhelming impact that has been so significant. And just to, again, show you how important these effects are from a geological perspective, atmospheric CO2 levels. These are the highest levels probably for the last 3 million years. Atmospheric methane, certainly highest levels for 800,000 years, possibly further back than that. Reactive nitrogen, the highest level perhaps for 2.5 billion years. So these key indicators of environmental or planetary change basically are the arguments that we're using for proposing the Anthropocene at the level of series epoch, in other words, terminating the Holocene. However, not everybody likes to see the Holocene terminated. This is because there are conservative influences within the bureaucracy that determines changes to the timescale. Two papers have come out quite recently, and this really was the inspiration for the title of this talk. A practical solution: the Anthropocene is a geological event, not a formal epoch. And this was followed up by the same authors, the Anthropocene as an event, not an epoch. Now, these two publications could rather easily be dismissed, except for the fact that the lead author, Phil Gibbard, who is actually a good colleague of mine, is Secretary General of the International Commission on Stratigraphy. And one of the authors, Stan Finney, is Secretary General of the IUGS, two very powerful bodies that are very influential. So these critiques of the Anthropocene need to be taken very seriously. So we within the Anthropocene Working Group have been analyzing these two papers and analyzing the concept of the Anthropocene as a geological event rather than a formal epoch. Now, a geological event is an informal term. It represents an informal unit, which would not then justify its appearance on the geological timescale. So this has serious consequences for what we are trying to do. This is from their publication from 2001. It shows the Anthropocene prospectively extended back to, well, maybe 50,000 years, back to the megafaunal extinctions. This is what they say about their geological event. They define it as the aggregated effects of human activities that are transforming the Earth system and are altering the biodiversity, producing a substantial record in sedimentary and in human modified ground. Well, I mean, that's fairly innocuous. However, that carries on. It discerns cultural and historical differences, socio-political divisions and economic inequalities at a variety of scales. For example, households, communities, society, and so on. It incorporates various historical and social processes. For example, urbanization, colonial violence, industrialization, capitalist production, and so on. In spite of all this, it claims to be stratigraphically robust. How can that be? Okay, so the Anthropocene Working Group's response to these two articles is in preparation, with two publications already prepared. One is being revised and the other one is about to be submitted. And these responses have been led by myself. The so-called geological event of Gibbard et al., as far as we are concerned, isn't actually a geological event. It is an interdisciplinary concept that interfaces with the geological record only through a highly interpreted and dynamic filter. It cannot possibly be stratigraphically robust. It's not really even strictly geological. In trying to satisfy so many different communities and constituencies, I feel that it has lost its focus to the point where it cannot really be useful within the earth science community. They regard their event as an event, but we see it actually as being closer to an anthropogenic episode, where episode is a classification used in the sense of the North American stratigraphic code. One of the objections that Gibbard et al. Have is that an Anthropocene series, an epoch, as we within the Anthropocene Working Group are proposing, would necessarily consign significant evidence that attests to human modifications of the Earth's surface and systemic functioning to one side or other of an agreed boundary. But all timescale boundaries do this. You know, any timescale boundary at a fine enough scale will be somewhat arbitrary. To give you an example, the middle and late Holocene have now been defined formally, and their boundary, the base of the Megalaean stage, is defined at 4.2 thousand years from the year 2000. Well, it just so happens that the very famous temple staircase at Tel Mozan, this is in the ancient city of Urkesh in Mesopotamia, which is now northern Syria. The boundary actually cuts right the way across the temple staircase. Any boundary, you know, any geological boundary, if you go at fine enough resolution, it is going to cut arbitrarily through one process or another. So using this as a reason to not define the Anthropocene as a chronostratigraphic term really makes no sense. This is arguing against the existence of a geological timescale. It makes no sense whatsoever. Okay, having said all of that, we think that the if you like, the event approach of Gibbard et al. Could be useful if it were named differently and defined somewhat differently. It's really, their event is really more like an archaeological period. Now let's take one archaeological period. Let's take the Neolithic. Well, the onset of the Neolithic occurs in the latest Pleistocene in the Near East. It occurs in the early Holocene in North Africa and the middle Holocene in Northern Europe. Now, no one would argue that the Neolithic is a useful term. Of course, it's a useful term, and all archaeologists use the term Neolithic. But the terms Pleistocene and early Holocene and middle Holocene, these terms are also useful. So the point here is that the two sets of terms complement one another. One is not more important than the other, both are needed. And this is our approach. We need an Anthropocene that is formally defined, but the event approach of Gibbard et al., if differently named and differently defined, could also be useful. So this is how we see the Anthropocene. In fact, by looking at the Anthropocene from a geological event perspective, we recognize an array of geological events all clustered around the mid-20th century. So we can use an event approach to define a chronostratigraphic Anthropocene at its base. This, incidentally, is the so-called geological event of Gibbard et al., and we would call this an anthropogenic episode. And essentially then, we are defining we call this the Great Acceleration Event Array. And it essentially aligns with Earth system science. And so it connects Earth system science with geological reality, with geological data and observation of sedimentary successions. So how is a new unit in the geological timescale actually defined and approved? Well, this happens by the definition of something called, or selection and definition of something called a global boundary stratotype section and point, a GSSP. And this defines the base of any unit on the geological timescale. The top of that unit would be defined by the base of the superjacent unit. Okay. So this is kind of how it works. This is the International Geological Timescale, and all units are defined. There's the Chibanian. Where's the Chibanian? Is just there. The Chibanian stage is defined now by a GSSP in the Chiba section in Japan. Japan's first GSSP. So all units of the geological timescale either are or will be defined by a GSSP, a global boundary stratotype section and point. The work is ongoing. 78 GSSPs defined so far, and another maybe 20 still to go. How does the process work? Well, in the case of the Anthropocene Working Group here, we have at the moment perhaps as many as 12 candidates. And of those 12 candidates, only one will be selected. And that will be selected by the Anthropocene Working Group. And that candidate, or the proposal based on that candidate, will then go up to the International Commission on Quaternary Stratigraphy, the SQS. That subcommission has to vote on that one proposal. And it has to receive 60% at least of the total votes. All votes actually within this process have to achieve a 60% supermajority or more for approval. The proposal will then go up to the International Commission on Stratigraphy, and if approved by voting, finally goes up to the Executive Committee of the International Union of Geological Sciences. And then that body would ratify the proposal. And when that happens, there is publication of the proposal in the IUGS journal episodes and a GSSP ceremony. So that's the bureaucracy behind it all. Now, I mentioned there are approximately 12 potential candidates. I don't want to go into any of the details of these, but I want to give you a quick snapshot of each proposal, just to give you a general idea of the proposals that are being prepared. And you can see they come from around the world, and they represent different environments. These are the different signals that are being looked at for each of those 12 candidates. You can see there's a number of different signals that are being examined. They include, for example, lead isotopes and carbon and nitrogen stable isotopes, fly ash, metals, microplastics, and so on. You can see them all listed here. Also various kinds of fossils as well. And depending upon the site, it will determine which particular analyses will be conducted. For example, one of the sites is an ice core from Antarctica. Now that will have certain analyses that a lake sediment may not have. So at the end of the day, even though only one of these candidates will be selected, they all contribute to the larger body of information, of stratigraphic information on the Anthropocene. So all of these studies are all important. I'll say something about the plutonium-239 bomb spike. This is really important because this potentially could be the main way of recognizing the base of the Anthropocene from a stratigraphic perspective. The plutonium-239 is released from thermonuclear devices in the atmosphere. And the thermonuclear devices produced vast amounts of bomb fallout material, which leaves a trace within the sedimentary record on a global scale. And this fallout occurred in the space of months. So the signal is essentially, from a geological perspective, essentially isochronous, essentially occurring at the same place, at different places at the same time around the globe. So we are looking specifically for plutonium-239. So again, I won't go through all of these in detail, but they include Crawford Lake in Ontario, which is in fact a 40-minute drive from Brock University. And so I'm actually involved in this particular proposal. This is a lake deposit, and you can see annual laminations that allow sampling of this lake core at annual and even sub-annual resolution. And we do have a very nice plutonium-239 signal from that core. We have Xihai-Long-Go-Wan in China, a lake deposit. This is a lake within a caldera, a crater of an extinct volcano. So you have deep anoxic conditions at the bottom of this lake, and you have annually laminated sediments as well. Searsville Reservoir in the United States. Again, you have somewhat annual resolution. There are some missing layers, but again, it's producing an interesting set of results. San Francisco Bay in California. Again, interesting for different kinds of reasons. In this case, you have lots of invasive species, especially from the 1950s, well, right the way through actually, a record of invasive species going all the way back to the late 19th century. And they're all very well dated. So each one of these sites has its own particular strengths and weaknesses. Beppu Bay in Japan, of particular interest, I'm sure, to this audience. I don't know too much about Beppu Bay, but it does have annual resolution. I have some colleagues that are working on this core, and it seems to be very promising. East Gotland Basin within the Baltic Sea, again, annually laminated, and people are working on this for various indicators, including microplastics. Flinders Reef in Australia and the Gulf of Mexico in the United States. In this case, the medium that is being examined is coral reef, and the corals themselves show annual lamination, and one can look at the annual layering in these reefs, in these coral reefs, to determine changes in water properties, in water temperature and water geochemistry over time. Ernesto Cave Speleothem in Italy, again, annual lamination, and with very fine sampling, one can determine changes in atmospheric conditions on an annual scale going back over many centuries. Palmer ice core in Antarctica. Of course, an ice core has the advantage in that it traps gases, atmospheric gases. So you have a direct insight into gases that were circulating over the past, 100 or 200 years. And then there is a peat deposit in Poland, which is also being analyzed. The advantage with the peat is that it is in direct communication with the atmosphere, unlike a lake where the signals in a lake deposit, the signals have to go through the water column before they reach the bottom of the lake. So there is some filtering of that signal by the water column itself, whereas with the peat is in direct contact with the atmosphere. All of these different media and these different localities, they all have their strengths and their weaknesses. So finally then, this is the Haus Culture und der Welt in Berlin. It is a world famous institution. It has a large amount of money, a large budget for funding projects that it considers to be interesting for one reason or another. And for one reason or another, they decided that the Anthropocene was worth funding, and they provided almost €1 million to fund most of the analyses on these 12 sites that I've just talked about. So if you were wondering, well, where does all the money come from? Well, it came from Haus Culture und der Welt. In fact, as I speak right now, there is a major symposium hosted by the Haus in Berlin, where the Anthropocene Working Group is reviewing the latest progress on all of those 12 candidate sections. And later this year, there will be a vote within the Anthropocene Working Group to select one of these 12 candidate sections. Once that is done, then there will have to be approval by the Subcommission on Quaternary Stratigraphy, the International Commission on Stratigraphy, and finally ratification by the Executive Committee of the International Union of Geological Sciences. Now, assuming there aren't any political obstacles, and of course there are always political obstacles in any kind of activity that involves normative science, but assuming there are no major roadblocks, then the Anthropocene will be an official unit of the geological timescale by this time next year. So thank you very much for your attention. I'll be very happy to answer any questions you may have.